Happy holidays, everybody. We started off the year with consensus, we switched over to time series, and my original intent was to wind up time series with the end of the year. Looks like we're going to run about a month over. I just had too many great interviews. We can always revisit if need be, but it's time to have a new season round about February, I think. Speaking of revisiting, this special revisits 3 mini episodes from the past. And no, it's not like a Dickens thing. So for new listeners, back before we did seasons, the format of the show was a little different. I'd basically every other week have an interview or this mini episode where Linda and I would discuss some topic. And those episodes were always meant to be like explainers, introductory episodes. And this first one we're going to kick off with is jam-packed with topics. Although I do think it's a good episode, I'm glad we're replaying it. It does stress one of the challenges I had in producing these episodes that we'll revisit later on in this. But first, let's listen to something with a bit of foreshadowing, actually. This mini episode on autocorrelative functions was recorded back in 2016. And if you listen carefully, you can hear the seed of the idea of doing the time series season, 5 years before we actually did it. There's also some mentions of visualizations in the show notes. Those are in the original show notes, not today's show notes, and there is no need to go hunt them down. They don't add a whole lot. If there's a visualization that our audio descriptions isn't satisfactory for you, just use a Google image search. It's probably better than my 10 lines of matplotlib code anyway. Oh, and one last thing before we get into this blast from the past. Can I just say, I love this version of the theme song. I'm glad it's back.
Data Skeptic mini-episodes provide high-level descriptions of key concepts related to data science and skepticism. Today's topic is autocorrelative functions and correlograms.
So, Linda, do you know what a time series is?
Is it a series of date and timestamps?
Yeah, you pretty much got it. Shortest episode ever.
Yes.
Time series is any data set or series that has a measurement of the same process or signal through time, usually at regular intervals.
So, what's a process?
A process can be anything. It could be like the price of a stock is a time series, right? You measure it every day in the morning or the average or whatever. The number of cups of coffee an office consumes in a day is a time series. The number of observed solar flares is a time series.
Yeah, so the first thing that comes to mind is measuring temperature.
Oh, it's a good one. Yeah, actually that has some really good properties for talking about time series stuff. Where'd you grow up again, or where did you go to college?
I grew up in Florida.
Yeah. Well, Florida has basically flat weather, just like we have here. So let's talk about where you went to college. Oh, no?
It got freezing.
Oh, really?
Yeah, there would be ice crystals on the grass during winter.
Oh, so tell me in a few sentences what the weather's like in Florida.
I don't know what it's classified as. Subtropical?
But I mean, if someone had never heard of Florida, what would you tell them to expect?
Oh, it's like high humidity, so like 100% humid.
Mm-hmm. What about just the temperature?
Well, I don't remember exactly, but during the summer, the average high is probably like 80, 90, and sometimes 100. The winter, I think the average high was like 70 or something.
That's not that cold.
Well, the thing is, I remember wearing shorts during the winter and just threw on a sweatshirt.
So we can describe time series in a couple of ways. They're often like a composition of stuff. So what we want to work our way up to is something called a REMA, but we won't get to talk about that today. But you can imagine that a time series is some sort of trend, right? That like it's going up or down. It has seasonal components, as your weather example does, and it has some sort of noise. That's the fluctuation you can't explain, which we call the residuals. You were just describing the temperature in Florida in a seasonal way, right?
Yes.
So what would be a good way if I just said, it's July 4th? What would you guess the weather would be based on the time series alone?
In Florida?
Mm-hmm.
I mean, I don't remember, but probably 90s.
If you had to guess a particular day and you had all the historical weather data, but you couldn't like check a thermometer, what would you guess the next day's temperature would be?
Oh, still 90 degrees Fahrenheit.
All right, so imagine it was any random day of the year, and I gave you all of the historical weather and asked you to predict today's weather. What would be like the most useful information in the whole history?
For me to make the correct guess?
Yeah.
Time of year.
Yesterday's temperature is pretty similar to today's, right?
Yes.
And even today's temperature 2 days ago temperature is similar to today as well, would you say?
Yeah, so I guess you could
3
just...
days?
Well, the weather people, we just look at the day before.
Yeah. Do you think 7 days ago relates to today at all?
Yes.
What about 70 days ago?
70?
Yeah.
Well, it does relate, but it's harder because then the season changes.
Really doesn't relate that much. Just much less than 7 days.
Yes.
Well, what about 365 days ago?
Well, that's helpful
Yeah,
because that's
really
actually
helpful.
like a year ago.
Yeah. So time series has these interesting things. It has, one is the autocorrelative, like the local thing, how it would be in a moving average, like how it relates to the recent days. But then there's also patterns that show up in time series. Weather, like a year ago, makes sense, right? In other systems, like maybe retail sales, do you think there's any regularity to retail sales?
Christmas shopping, New Year's, Thanksgiving, Black Friday.
So once a year, big spike in retail.
Well, I feel like when they change seasons, they probably have big sales, which encourage people to buy and get rid of inventory.
Maybe they have the biannual weekly sale or whatever they have. Yeah, the blue ribbon sale, something like that.
Yeah.
Do you think today's total revenue at a retail company would relate to yesterday's?
Yeah.
Actually, it would, but you know what's probably a better predictor? 7 days ago, right? Cause
you want the same day of the week.
Yeah, because day of the week has a strong effect. So that's what's called a lag.
Do you want to tell me what a lag is?
So lag is a number of days. It's a certain time between your current observation and previous ones. In the case of like temperature, you notice that yesterday really strongly predicted today, right? Or it's very similar temperature, most likely. Most of the time, we don't have big jumps. So that's a lag of 1. But in the retail sales example, you probably expect a lag of 7 because in order for you to see a repeat process, you'd expect 7 days since there's such a weekly effect there, right?
Yes.
So we would like to have a nice way to quantify this, wouldn't you think?
Quantify the lag?
Quantify how autocorrelative a function is in terms of its lag.
Okay.
So let's think about your weather example here. So I didn't know you were going to say Florida. I thought you were going to say Chapel Hill where you went to school. So that's the data I pulled here that's in the show notes. This is a plot of Chapel Hill's weather. Can you maybe describe it, given that this is not a video podcast?
Yes. It looks like 6 little hills that are steep.
Going back 6 years then, huh? Or what do you mean by they're steep? Well, because that's an annual effect.
Oh, this is annual. Oh.
Well, it just so happens that when I plot it like this, you can see the annual trend. That it's very cyclical, right? The troughs, the cold temperatures are the winters, and the high temperatures are the summers.
Oh.
But it's not smooth, is it?
Yeah, it goes up and down.
Yeah, even within the normal seasonal effect.
Yeah.
That's just sort of noise in the data that we can't explain alone by sort of the day-to-day trend. We'd like to take the autocorrelative function, which is a measure of how much it correlates with itself. And there's a special type of plot. So if you scroll down, you could see a plot. Have you ever seen anything like that one?
No.
Well, let me explain it to you. I'm going to come over there. There you see the lags going out for almost all those years. Now, this is a autocorrelative plot. It's kind of hard to describe, but what do you see?
Well, there's an axis that says 0. Then it looks like wavelengths that go up and down.
What this shows is a horizontal line for every day saying how much that day correlates with the current measurement. So correlation, when we talked about in previous episodes, of 0 means there's no relationship. Correlation of 1 means that they're positively correlated. Correlation of -1 means they're completely negatively correlated. The reason you see that wavy pattern is because, as you identified earlier, very recent days are very highly correlated. But the longer you go back in time, the less correlated it is. But in the case of weather here, you get this interesting phenomenon that at a certain point, you're at the opposite cycle of the season, and it negatively correlates with the present. This also has a property that's a little deceptive, because here it looks like all the recent days are all very correlated, which they are mathematically, but wouldn't you like to know which one correlates the most?
Yeah.
So they introduced this thing called the partial autocorrelative function. What its purpose is, and it's below, is to help you understand what's called the AR parameter, so how autoregressive this is. So here you see, maybe describe what you see here.
Oh, the first 2 lines are very high. They're almost at 1. The first one's at 1, and the second one's just right below 1, so like 0.9 or something.
So you know what this teaches us? that if you want to predict the weather, the most important day, so the day, yesterday, is the most predictive day. And then 2 days ago, not very helpful in predicting the weather.
Depends where you live. But for North Carolina has much more variability than LA.
So that one's kind of interesting, right? It tells us a little bit about the autocorrelative lag involved in weather, at least for that city. I did one more that I thought was interesting. We're putting in an offer on a house, right?
Yep, exciting.
So I went ahead and looked at the prices in that neighborhood. Is this something that might be interesting to you?
I'm interested.
All right. So this first plot is the price. What do you see there?
This is an X and Y axis. So the bottom X axis goes from 2011 to present, it looks like. Mm-hmm. And then the Y axis says median sale price. So it ranges from 200,000 to 800,000.
Oh, so this, to be clear, what we're looking at, this is the average listing price. So it means it's what people are saying they want for the house. So hopefully that goes up, right? But we'd like to know, is there a trend? Is the neighborhood moving up? Regardless of if we make the home better.
The trend appears that it is moving up. However, there's such a greater range of, it's almost like less stable.
Yeah, there's a range here. One thing we'd want to do would be to detrend this data. That's something else we'll have to talk about later. Because if you look at home prices in the whole country, they're all going up. So we should subtract that out because if we're just going up at the average rate, then we're actually staying at zero. And I haven't done that sort of analysis yet because this is all about autocorrelative functions. But I think we could do like 8 mini episodes on this topic, and maybe we will if we get this house. We can do a lot of time series stuff. That can be a new era for the Data Skeptic podcast. But below is the autocorrelative function. So what the next plot is telling us is how much the price of homes varies by the prices from days gone past. So just as we saw with weather, the most relevant estimates are recent days. So recent days best predict the current day, and then it declines with time.
The day, you mean the cost?
How well the prices are predicting the next day's price.
So what is it correlated with?
So this compares the current day's price on any given day to what the average price was the day before, and the day before that, and the day before that. And every day before is an additional lag. This shows us exactly why we want the partial autocorrelative function. So if you scroll down to the next one, and here we see similar thing to the weather, that it's the most recent day that is the best predictor. It has all the information about the moving average trend. Interestingly enough, there doesn't seem to be like a 7-day effect here or anything like that. The day of the week that you listed on doesn't have an impact, but that makes sense, right? It's not like Wednesday is a better day than Saturday to list your home. People do it when they do it.
Yeah.
Or at least it doesn't affect the price. It's not like, we can have an open house 2 days sooner, so we'll charge more for the house. So what we see here is, the 2 most recent days are the best predictor, and after that, not so much.
Well, it seems like even around the first 100 days, they vary a little bit further from the zero line. Yeah,
but there are very weak correlations and probably due to statistical noise based on the boundaries that you see there.
So these boundaries are statistically not significant?
Yep, anything less than that is considered statistically insignificant. Doesn't mean it's not a real correlation, just means it's not statistically significant. The effect size could not be measured by the available data. So the effect size is either very small or doesn't exist. So, in the future, we can get into more of the seasonality stuff and talk about ARIMA and ARMA, but this is a starting point. What's your first takeaways from your first experience with time series?
I don't know. I will say this partial autocorrelative graph, I feel like you should change the scale then.
Yeah, what should the scale be?
If this area in red is not statistically significant, then visually, I do not care.
The following message comes from Data IQ, the platform for everyday AI. Let's face it, the potential for positive change with AI is huge. But seeing that value is hard. AI-driven growth is about organizational transformation, not just technology, and today's businesses struggle with the complexities of bringing AI innovation to fruition. That is where Data IQ comes in. Infusing a culture of working with data and AI every day and at every level of the company. Whether solving for the mundane, like automating forecasting, or what is the optimal number of widgets to buy, or understanding moonshots that push the limits of today's technology to grow your organization and innovate. That's Everyday AI. Join more than 45,000 people worldwide across banking, insurance, pharmaceuticals, manufacturing, retail, and more who are driving results with Data IQ. Visit dataiku.com to learn more. That's dataiku.com.
I'm Jeff Wheelwright, tech journalist and host of the ARM Viewpoints podcast. Along with ARM, the company whose technology sparked the mobile revolution, we're bringing you the latest from the heart of the tech world. I've had fascinating conversations with industry experts about topics ranging from AI and data security to the promise of 5G and the future of healthcare, and we're just getting started. Join us as we explore the evolving world of computing. Download and subscribe to ARM Viewpoints at Apple Podcasts, Spotify, Google, or wherever you get your podcasts.
So we did get that house that I mentioned. Or actually, that might not be true. We had to do a bunch of bidding wars before we got our house. But the whole process, that is to say, that brought us to our current home and the current garage I'm in, which is and has been since the start of COVID, the recording studio where I've recorded every Data Skeptic interview for the last, 2 years or so. When it became clear that the pandemic was a long-term thing, we let our office lease go. And it's been a good run in this garage. But I'm looking forward to figuring out how I get back out to conferences and meeting you guys at some point, hopefully next year. Anyway, when all the work we do for our clients is in the cloud, it's pretty easy to be remote and distributed now. But anyway, back to more, perhaps innocent times. This next mini-episode, also from 2016, Stationary Indifferencing.
Data Skeptic mini-episodes provide high-level descriptions of key concepts related to data science and skepticism. Today's topic is stationarity and differencing.
So, Linda, I was pleasantly surprised as we prepped a little bit for this to find out you actually have a lot more experience with quality control than I thought you might.
Well, you never asked.
Well, I've mentioned Schuhart charts a couple of times. You never really spoke up.
What are they called?
Schuhart charts
I have no idea what that means.
is a thing for control systems. What does stationarity mean to you, just off the top of your head? Obviously, it's a version of stationary. What is stationary?
Stationary?
Uh-huh.
Well, there's stationary like what you write on.
Oh, yeah, not that.
And then there's also stationary of like not moving.
Yeah.
A stationary object is one that's not moving.
Yeah, so that actually is a pretty good intuition for the statistical meaning. It's a function that is not changing through time. So let's get into quality control. You actually have a couple of experiences, right?
So wait, we're moving into quality control because why?
Because I want to relate quality control to stationarity. In previous jobs, you've had experiences with quality control, right? Once with some products that were being developed and once with an audit of sorts.
Yeah, so I used to work, I'm not going to name names, but I used to work at a coffee shop, and then they would measure their quality control because they would have mystery shoppers who would come in and buy this product, and then they would measure it based on, let's make up an example. For example, it could be a cup of coffee. So they could order a latte, then they could time you and see how long it took for you to make the product. Then they could take the temperature and see if it was delivered hot enough, because if it's cold, that's not optimal. They could grade you on taste, grade you on whether you enter the customer service aspect, whether you talked to them or knew them or acted friendly. And then in terms of like giving them the correct change in money, they could grade you on that. So that's one example how a mystery shopper can gauge this. All in secret, by the way.
How often do the mystery shoppers come?
In this industry, they said once a month. And it was always you would never know when, what week or anything.
Once a month is a little bit rare. Why wouldn't they do it, let's say, 8 or 9 times a day?
8 or 9 times a day?
Yeah, once an hour.
Well, I would say
measurement. What if the morning differs from the evening?
That's probably just expensive more than anything.
Yeah, it's expensive.
Then you have to get however many mystery. If you want to do it once an hour, that means you need like, if they're open 8 hours a day, 8 different mystery people.
Yeah.
Unless you want them to repeat it, in which case that could look suspicious.
Yeah. So you'd have to get a lot of different people. How else are you going to know the complete picture of the business? What if the afternoon shift people are starting to nod off? They're not as attentive as the morning shift? Or
I mean, that's why it's random times, once a month, or you could do it once a week or so. But I think most people make the jump that if you do it randomized, that maybe the rest is probably okay. And then also you probably keep people on their toes knowing that it's random.
What if you send the mystery shopper and then the day after that, the employee is like, phew, they're not going to come for at least 3 more weeks because they only come once a month. So we can slack off now.
Once the mystery shopper comes, it's just a set amount of time. It doesn't mean the next mystery shopper isn't exactly a month. And they may not give you the report right away.
Ooh, okay.
To like keep it in the dark.
Could you ever guess the mystery shopper?
I mean, you might have habits. You would know the mystery shopper is going to buy this one thing.
How do you know the one thing?
Because they told us.
The mystery shopper will always buy it.
Well, because at this business, they named this one product, if it was a drink, let's say it's a latte, that could be your standard. And that's the one that you're judged on the most because they deemed it as incorporating all the elements that they viewed as important.
But then when they pull out a stopwatch and time you, isn't it kind of obvious they're the mystery shopper?
Well, they're supposed to be secret.
Oh, okay. So
they don't show you that they're doing it. It's all secret. You don't see anyone.
Did you ever catch someone being not as secretive as they should? Oh,
you don't see anyone.
So it's a pretty good measurement then. Given your experience and observing your coworkers, did you find that they always had a pretty consistent quality of work because they were afraid they never knew when the mystery shopper would come?
So was anyone slacking off? I mean, I think everyone was always on their feet and on their toes watching out because they were like, and they would give each other feedback too. They'd be like, oh, that drink wasn't very good. You need to remake it. I mean, there was a level of quality that you guys had to attain to.
So if I had come into your store at a random day, do you think I would have gotten a pretty consistent quality? Or maybe would the weekend shift be better than the weekday shift?
I mean, it really just depends who's working behind the bar, but generally they try to keep the experienced people behind the bar so that, consistent.
Yeah.
Predictable workers. That's another reason why they probably want to maintain the same workers. So it's a consistent team.
So why do you think all those things would be valuable to a business?
Well, it's dependable, right? So if you're a large franchise or a chain, you probably want people to know that when you go and eat and drink there, it's the same standard.
Yep.
Everywhere.
Yeah, and the mystery shopper should be able to audit at any time, and they can expect a consistent experience that the average is always the same, and a known variance that, the quality, yes, it's not maybe precise every time, but it's within a certain range. The line could be a little longer, a little shorter, or whatever. For those who already know about this sort of stuff, I will also say that the covariance must not depend on time. But if anyone doesn't know what that is, don't worry about it, because I want to get into just more the gist of stationarity. So if your process is stationary, you get to take advantage of lots of useful statistics, in addition to the value just being consistent, plain and simple.
Okay, so you gave us some food for thought about how to control for certain things and then how to measure the variance of others.
Right. So not all processes are stationary, like maybe your assembly line. But if we do a process called differencing, then they often become stationary. Differencing is the process where you subtract the most recent observation from the previous one. So it's kind of like you take out the difference from yesterday and you just want to study the change. And sometimes there's a reason why you might study a differencing with like 2 legs, but for the most part, differencing means you just take yesterday out of today. So you're looking at the day-to-day change. That often gives you a stationary process, which allows you to make really useful predictions and do inference. So we get all the benefits of a lot of known things like the central limit theorem, which we talked about a long, long time in another mini episode.
A long time ago.
Yep.
Yeah. Oh, well, I don't really remember that. But in terms of quality, I know there's some podcasts I like more than others.
Yeah, which one do you like the most?
Oh, I like the one about me busting my knee open.
Yeah, that was a good one. Yeah.
And then I think there was a long episode one that we listened to together. Oh, I like the cornbread one.
Yeah, so you remember that, but you don't remember central limit theorem.
Nope. So, I mean, how do you make sure your podcasts maintain a standard?
So how do I measure quality control of the podcast?
Yeah.
Do I want a stationary quality measurement?
I don't know. I assume so.
Well, actually, I would like it to be improving.
Okay.
but like, and I hope the show is improving, but then if it's improving, then it's not stationary. But if I want to study it and make sure that I'm not wavering, that I have a really tight variance, then I might do this process called differencing, where I just compare this podcast to the last one and I see how the relative change in quality. So I'd first have to find a way to get a really good measurement of the quality of the podcast. Maybe we could rely on your memory if we assume that the better episodes are the ones you remember more, something like that. Does that seem like a good way to measure the quality?
Well, I'm a biased person, so no.
But you're my audience. I'm trying to convince you.
I'm only some of your audience. Some
Right.
people like me, some dislike me. I hear you loud and clear, people out there.
If we take for granted that the podcast is improving as I get practice and work harder at the show, then I would want to use differencing to take that out and just study the week-to-week ups and downs. And that is hopefully a stationary process. And then I can look at quality control measures. And I get these benefits that it has an average, a known variance, and that property of the covariance, that gives me a stationary distribution, which has all these nice little properties like central limit theorem. That's partially why stationarity is very important. It allows us to do inferencing and make good statistical predictions on a time series that happens to be stationary or one we can make stationary through differencing.
I think on this episode, I kind of just learned how data scientists view quality control.
How do we view it?
You just use different vocabulary.
But we view it statistically.
But we didn't really go into statistics here.
No, I talked about a lot of statistics. Well, anyway, lots of that is fodder for future mini episodes, including a discussion of integrated time series and the Dickey-Fuller method for checking stationarity. Now, we never did get around to doing that mini episode on the Dickey-Fuller method for checking stationarity. And I'll go ahead and say at this point, we are never going to, although I'm going to do some future mini episodes with Linda from time to time when we can schedule it. I don't think anyone needs a mini episode on the Dickey-Fuller method. No disrespect. I love doing that format, but at a certain point it got stretched. Part of what made it work, what I liked about it, was Linda's sort of casual indifference to a lot of the topics. She wasn't an aspiring data scientist, not at all. So that kept me honest. I always had to figure out a way to make the material interesting, or it wasn't a good fit for the show. And the other lesson I learned is sometimes it's just not super relevant for a non-technical listener. So as we've gotten into more of pure interview formats, of course, we've gotten a bit more technical. Some of you like that, some of you don't. And we're going to try and measure that a little bit better next year. I have this whole survey thing we're going to set up. You'll hear more about when it's ready. But while I go back to working on that, I'll leave you with one more episode from the archives, staying in line with our time series season. For some of you, this is new. For a lot of you, it's new, actually, if you look at the download numbers. But for some of you, you may remember our last installment for the evening, Heteroskedasticity.
Data Skeptic mini episodes provide high-level descriptions of key concepts related to data science and skepticism. Our topic for today is heteroskedasticity. How do you pronounce it? Heteroskedasticity.
That's pretty good, actually. Before we get directly into our topic, I just wanted to explore this particular data visualization that I saw online. Listeners can also see it in the show notes for this episode. Maybe you could just describe in your own words what you see.
There is a graph. What does the x-axis represent?
The average household income, presumably for a particular zip code or city that this data set is based upon.
And then what does the y say? I don't understand.
That is the average number of tickets issued per person in that geographic area. Tickets from the police, obviously.
So from this chart, it looks like the more money you make, the less traffic tickets you have.
Well, there's also one thing that's implying that. What is present in this chart that might make you
there's
think
a
that?
line.
Yeah. So if the line wasn't there, can maybe you block it out in your mind, and what do you see then without the line?
I don't know. I just see a bunch of dots. It's hard. It seems to suggest, though, as you make more money, you just get less tickets or something.
Yes, indeed. So there is absolutely a claim here. I would say that the person who created this graph is making the claim more traffic tickets are issued per person in zip codes with lower average income. Now, I have a lot of problems with this graph, and I thought it would be fun to talk them through and look at some of the assumptions. This is charting the household incomes of people against the number of tickets in those geographic areas. So we could be falling into something called the ecological fallacy, but we'll leave that for a subject for another mini episode. That's why I make the point of saying you could live there or you could be driving through there. This is just measuring the amount of tickets issued and then comparing it to the population there, which are not necessarily the same people we're talking about.
When I was younger, I didn't make much money.
Mm-hmm.
And I'll admit, I got more tickets.
Well, there you go.
I was a not as safe driver, and I made more erratic decisions, and I was not patient.
So you make more money now and you're better at issuing bribes. Is that what I'm hearing?
So nowadays, I make more money than 8 years ago, and I'm definitely a much more cautious driver because I've had so many tickets in the past. I've just decided that tickets aren't worth it. So I just don't like to speed. If something doesn't seem safe, I wait. I'm much more patient. And so, yes, I make more money, but I think the solution is that I'm just a more experienced driver.
Maybe we would say that higher income correlates with older age, as does responsibility in driving. Could that be the case?
Yeah, I mean, we could all admit there's a high percentage of 16-year-olds that get tickets.
Yeah.
And car accidents.
So looking at it that way, this relationship seems plausible. Like I said, I have some problems with this plot, and I want to first call out something called Hyman's categorical imperative, which says that before you investigate if a phenomenon is true, you should first establish, is the phenomenon even real? Here's one of the problems I have with this plot. This makes a linear assumption. It assumes that the right model to describe this is that as incomes goes up, that the chances you'll get a ticket goes down.
Linear?
Mm-hmm.
I don't think it would be linear, no.
Yeah, so I don't think it'd be linear either. And this is an oversight I see a lot of people make. They'll go into Excel and they'll add some just trend line without establishing if the underlying data appears to be linear or not. Actually, let's just talk more about what the plot shows. So the dots are the actual data. That part's pretty clear, right?
Yes.
And we could say the line is the person's model. That's what they think is the relationship between average household income and the chances of getting a ticket.
I mean, if you think about the average income, there's just more people who make the average income than people who are at the higher tiers anyway, so.
Yeah, so this is definitely an imbalanced sample, and we're likely to have, it appears the creator of this plot just did an ordinary least squares regression. That's going to bias towards the most dense areas of data. Mm-hmm. It's going to be less biased by the outliers. Mm-hmm. So let's talk about some of those outliers. What do you notice about the data points of highest income, above about 85,000?
They're above that line.
Yeah, all of them, right? Another way to say that is that this model consistently underpredicts for all high incomes. Do you think that's a property of a good model?
Well, I don't know. You said on previous shows, if it's too predictive, it's a bad model.
Yeah, what you're referring to is the risk of overfitting. I definitely would not say this overfits the data. Does it underfit it, maybe? That would be the claim of assuming it's linear when it's not. But let's also look at the lowest data points. What can we say about all the data points making below 40,000?
Well, they're all above the line, too.
Almost all of them, yeah, all but two. It seems that this fit doesn't adequately capture incomes below 40,000 or incomes above about 85, leading us to believe that maybe a linear fit wasn't the best choice for this. Mm-hmm. Now, there's another thing we do more generally is we look at what are called the residuals. We've talked about that before, but I'm not sure if we talk about it enough. Do you know what residuals are?
No, but I would assume it means leftover.
Leftover after you subtract the actual observed data minus the model's prediction. So imagine each of those dots, the model's trying to predict those. Measure the difference between the dot and the line, and you get the residuals. That's the amount of error, what the model is not accounting for. So whenever there's a pattern in the residuals, that tells you that your model failed to account for something. Because if your model accounted for everything that's predictable, your residuals would look like white noise, just random data. That leads us to this other point. What I wanted to talk about here is heteroskedasticity. So heteroskedasticity is the circumstance in which the variability of a variable is unequal across the range of values of a second variable that it predicts. Is that a clear definition for you?
No, I don't know what that means.
Let's say you asked a bunch of people to measure a pencil, and they all had different rulers, right? Everyone has a different tape measure at home. How much do you think their measurements would vary?
Everyone's pencil is different length if you think of the old-fashioned pencil. But if it's a mechanical pencil, they're probably all the same length.
Yeah, so let's say they all have the same mechanical pencil. Although, good point, there's variance due to manufacturing, and there's also variance due to the measurement.
Oh, okay. They probably give or take, like 5 millimeters.
It'd be very small variance. That's the variance. Now, what if, on the other hand, you ask them to identify a neighborhood cat and measure its length from nose to tail?
So it's any neighbor's cat?
Yeah, any neighbor's cat.
Well, that will vary greatly.
Now, what do you think if we separated the cats by how old they were? Do you think there's as much variance in kittens as there are in adults?
I don't know. I don't look at kittens' tails.
So I'm going to go out on a limb and guess that kittens, there's less variance because they're all, there's a certain, maximum size of a kitten, right? I don't know what the biggest kitten would be, but even humans, no human is born 3 feet tall. So since they're smaller, there's less of a chance for variance there. Whereas as they get to adulthood, you start to see different genetic traits and breed traits where you can have really big cats like a Maine Coon and really small ones and stuff like that. Mm-hmm. So the variance in size increases as the age of the cat increases, up to adulthood, I presume. Mm-hmm. That is heteroskedasticity. It's when the variance is conditioned on some other variable, in this case, age. Heteroskedasticity is another thing surprisingly, actually, you can ignore it a lot and get pretty far because it generally won't bias a fit like the ordinary least squares regression we see here, but it does definitely screw up analysis of variance that we talked about kind of recently. Heteroskedasticity is one of those things you have to check for in your data and sometimes try and smooth out, like maybe with a logarithmic transformation or something like that. So truth be told, it's one of those things that's not the greatest crime to ignore, but it's something a good data scientist should be aware of in their data.
Is that bad?
Well, it's something you should account for. Data is neither bad nor good. It is what it is. As long as it's correct, it is the data. It's our analysis of the data that counts. And if you fail to account for heteroskedasticity, that is bad because you may arrive at a false conclusion because you're using a method that assumes homogeneity of variance across a data set. And if that assumption fails, then your analysis is on shaky grounds. Thanks as always for joining me, Linda.
Thank you. For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.